we haven't completely left mechanics behind, because there are ideas from earlier in our course that are still useful here. And hopefully they've been presented to you in such a way, and you've practiced them in such a way, that there's a kind of reasoning that makes sense. This idea here, there's an electrical effect that is observed. For example, if you take the plastic rod and you rub it with fur, there are electrical effects that you observe, and of course I parlayed that into an electric force because I can make objects move. Remember a demonstration, I made a can roll across the table. I produced an acceleration. An acceleration is caused by a force. There must be an electric force. We've identified it. We have an equation to calculate how much electric force we should expect in any given physical situation. But the thing about forces that we already know is that forces do work. I'm asking you to recall a lesson that probably seems like forever ago, when we talked about how forces can change the kinetic energy of an object by doing work. So forces do work, and work is not work in the colloquial sense. I'm at work right now teaching physics. No, work is in the sense of changing the energy. So there must be a form of energy associated with electricity. You see, it's exactly the same concept. There's a force that does work to change energy. What do you mean, energy? I mean, there's a number that you can calculate associated with the electrical effect that is measured in joules and is the electric energy. So I'm going to use capital U because this energy of electricity is a potential energy. The other energy is kinetic energy, the energy of motion. This is not energy of motion. The electrical potential energy would be calculated according to the work, which is force times distance. I have some electrical force, and a charged particle maybe under the influence of that force is moved through a distance. I calculate a certain number of joules. Well, the electric force is Q times E, I established in the previous discussion. The electric force is Q times E multiplied by D. QED is a number that I can calculate. A certain charge in coulombs, a certain electric field in newtons per coulomb, multiplied by a distance. So the coulombs cancel. This works out to Newton meters, which is a joule. Associated with the electrical effect, there's a kind of energy that you can calculate, a number that you can calculate. And it's not unlike the gravitational potential energy. It's an energy of position. I know this slide is very noisy, but I didn't want to go multiple slides with it, so let's compartmentalize it. Here, my equations. I've just said that the electrical potential energy is QED, and that's new. Never seen that before. It's reasonable because it's a force times a distance, which is a work, which changes energy. It makes perfect sense in our physics structure. But I'm also aware of the gravitational potential energy. Here I've labeled U sub G. The gravitational potential energy is mgh, and that is familiar. Yeah, gravitational potential energy is mgh. I remember that was on 12 sheet. That was in a homework. That was on a quiz. That was on the test. The gravitational potential energy, mgh. Well, look how they really are the same thing. The charge is the property of matter associated with the electrical effect, Q. The mass m is the property of matter associated with the gravitational effect, mass. The electric field, the gravitational field. Some distance in space in meters, some sense of space, some height in meters. It's very much the same equation, and here's why. Here I've drawn, on the left-hand side of the slide, a gravitational field downward. I've never done this before in our course. I've drawn a sequence of field lines directed straight downward that represent the gravitational effect. Invisible, but ever present everywhere, gravity downward. Now, if I have a massive object and I want to lift it in the gravitational field, lift it to a high place, I have to exert a force to lift it. There's a weight force directed downward, so I have to exert a force upward to lift it. And when I do, the work that I do increases the gravitational potential energy. I'm doing work to increase the energy, gravitational potential energy. You all right? I've drawn the electric field here horizontally from left to right, just because electric field's not a vertical concern. Electric field can point in any old direction. In a sense, the electric field's more complicated. That's not a scary idea, but the electric field here points horizontally from left to right. So if I have a positive charge and I want to move it to the left, I have to exert a force, because positive charges feel a force in the direction of the field. Just like a mass feels a gravitational force in the direction of the field. So I'd have to push it, and so I do work that increases the energy. The main difference between these two potential energies, the one that I'm familiar with and the one that I just learned about, is that negative charges experience an electrical force in the opposite direction. So the negative charge wants to go that way. If I want to move that negative electric charge to the right, I have to pull with a force. I do work to increase the energy. Because electrical forces exist, work is done, and the work changes the energy, which leads me to the electric potential energy, which is really the same equation as my gravitational potential energy. There's another fundamental difference that I've already alluded to. When I encounter electrical effects, there's usually so many charged particles involved that I might call it an uncountable number. When I encounter gravitational potential energy, I take a rope and I attach it to a crate and I wheel the crate up with a pulley, and then that crate is up somewhere high, and I calculate its gravitational potential energy, mgh, because it's a single object. My everyday encounters with gravitational potential energy involve a countable number of objects, so I can calculate the energy of this one, the energy of this one, and the energy of this one, and just add that energy together and have a certain number of joules. But when electrical effects happen, invisible electric effects, which are taking place around us all the time, most often there's a very large number of particles involved. And so we do a thing with electricity that we do not do with gravity. We create a quantity that is known as the electric potential. Here's a huge inconvenience. One slide ago, I defined the electrical potential energy. Now I'm defining a different quantity that is called the electric potential. Those names are so similar that it's going to take some effort on your part to keep them straight. On the previous slide, I defined the electric potential energy. V is called electric potential. See, it doesn't have the word energy on it. And that's apt to cause some confusion for you, unless you make a deliberate effort to appreciate that they're not the same thing. So it takes a heads up to do that. Well, Shiley, that was a very bad choice. Yeah, in physics, we've made some bad choices. Like, for example, when Ben Franklin decided to refer to resonance electricity as negative. That caused all sorts of trouble. That was a bad choice. But he had no idea because the electrical effect was invisible. V, the electric potential, is the energy per charge, because there are so many charges that calculating all the individual energies is not a practical thing. So instead, I describe electrical energetics, if you like, in terms of the energy per charge. And I don't have any reason when I'm talking about gravitational potential energy to talk about the gravitational energy per mass, because very often there's just one mass. Why would I do that? But here, the energy per charge, the energy measured in joules and the charge measured in coulombs, this is electric potential in joules per coulomb. It's a physical quantity that represents the amount of energy per charge. Now, you might see this for the first time and think, well, that's bonkers. I've never heard of such a thing. Now, all of a sudden, my physics has become very abstract, except that it hasn't. This quantity, the electric potential, is a quantity that you encounter every day of your life. Because the electric potential describes the energy per charge, there's an interesting effect here. I'm going to draw an analogy, and this won't be the last time, between the electrical force and the gravitational force in the context of water. Imagine that I have these two tanks of water here, and I've connected them with a pipe. From everyday experience, I know that the water does not flow from one to the other, because the energy on one side is the same as the energy on the other side. The energy per unit mass on one side is the energy per unit mass on the other side. There's no difference, and so there's no flow. But I think it's a matter of common sense that when I raise one and lower the other, such that one is at a potential that I might call high, and think if I raise a thing in a gravitational field, I increase its potential energy. If I raise one, I call that the high potential, and the low potential, water will flow from one to the other. You have to suspend a little disbelief here, because when the water flows to the other, this will probably overflow and it gets on the floor and runs off on. But if I raise one higher than the other, the water flows. And then if I raise them back again, the water flows in the opposite direction. Electric potential is abstract, for sure, the energy per charge. But if there's a difference between the electric potential at two locations in space, then charges flow from one location to another. And so I calculate that by measuring two electric potentials at two different locations. This one over here is potential 2, and this one over here is potential 1. And they're not the same. And as you know, we like to do in all of our sciences, I'll calculate the potential difference. Delta V literally means change in potential, right? Because delta always, in my physics, means change. So delta V is the change in potential, which I'll just subtract, which, surprise, surprise, is measured in volts. I agree that electric potential, at first blush, is abstract. But in your everyday life, you encounter outlets, like the ones around the outside of the room here, that are 110, 120 volts. What does that mean? It means between one prong and the other prong, one place and the other place. V2 and V1. There's a difference. And that difference is 110 volts. But the potential is measured in joules per coulomb. So a volt is completely equivalent to a joule per coulomb. So in our outlets that we plug all of our everyday devices into, there's around 110 joules per coulomb difference, one side and the other. One prong on the outlet is lifted, the other prong on the outlet is lowered, so that there's a difference. And when there's a difference, charged particles flow. And those charged particles flow through your electric device. And the change in their energy expresses itself in all of the wonderful things we've managed to do with our technology. Whether it's as simple as generating heat or creating circumstances inside of a microchip to do a calculation, as inside of your computer. It's the energy per unit charge changing that delivers the energy in the form of a flow of electric charge. And 1 volt of potential difference is equal to 1 joule per coulomb, energy per unit charge. And we talk about that because if you were to plug an electrical device into the outlet, we don't say, oh, I need to plug in my phone, I need 12 electrons. Because it turns out you need way more than 12 electrons to flow through your device in order to create the electrical effect that we enjoy with that particular technology. When charges move, what I've been referring to as the flow, I'm going to give that another name later on this week, but when charges move, it's because of electric field. Charged particles accelerate due to electrical forces on the charged particles. It's electric field that produces the force that moves the charged particles. Electric field. The field and the voltage are simply related. Pardon my algebra. The potential difference is in energy per charge, but I just defined the electric potential energy as the charge times the electric field times the distance. Charge divided by charge cancels, and I have a new equation, another relationship that is more abstract, but has to be true, because all I did was cancel the Q's. The potential difference is the electric field multiplied by the distance. Now, I already have an equation for electric field. I already have an equation for electric field, KQ over R squared. I already have an equation. Now I've got a new equation that doesn't involve just point particles, like two particles exerting a force on each other or creating electric field. It involves situations where there are many, many charges. I now have a technologically advanced equation for the electric field. Dividing both sides of my equation by D, the electric field then is the potential difference in volts divided by a distance in meters. So according to this equation, the units of electric field would be volts per meter, which is not what we said. If you were to flip back in your notes and look, you would find that the original units that we gave for electric field when I first proposed it were newtons per coulomb of force per unit charge. The units of electric field are still newtons per coulomb. That's still 100% true and a legitimate unit. And if you gave it and an answer, the electric field is 17 newtons per coulomb, I would have to accept that because those are appropriate units. The more common unit, because it lends itself more to technological application, the more common unit for electric field is the volt per meter. So if you answered the same question and said 17 volts per meter, those are equivalent. I have to accept both of those answers. It's really handy, though, to think of electric field as volts per meter because I can do calculations based on whether or not the units cancel and how all of that comes together. The potential difference is what we think of as voltage. And as we go forward with this material, we're going to change from talking theoretically about the nature of fundamental electrical forces between charged particles, perhaps within the atom, and start talking in a practical way about how we harness the electrical effect to do productive technological things to advance our human society.